Welcome to our presentation, Rage Against the Machine Clear, a systematic analysis of machine clears and their implication for transient execution attacks. This was a co-joint work between Hany and me, and also with the help of the professor of Herbert and Cristiano. And you saw Herbert yesterday on the keynote. And all of us are coming from the VUSEC security group in VU University, Amsterdam. The outline for today will be 4 main steps. We start with a small background section to catch up with the main concept. Then we'll explain the core of the slides that are about machine clears. Later, we also will show a full end-to-end exploit on Firefox. And finally, some conclusion and some recap and results. Okay, let's break a bit the ice. Who knows this image? Or, okay. Exactly. So the Dutch police managed to find people growing illegally weed in their apartment just by observing the melted snow on the roof. And why we brought this slide is this is a perfect example of side channel. So you don't see the guys actually growing weed, but with a side effect of, let's say, a secret information, you still manage to infer information. But obviously, CPUs doesn't grow weed. So how does it work on a modern processor? Switch to, let's say, a thermal side channel to a timing side channel. That is usually the most common one is flush and reload. Let's quickly explain it. So we have an attacker and a victim, let's say 2 different processes, that they share a common resource, the data cache in this case. The first step is to bring this array in a known state by flushing entirely the array from the cache. Then the next step is to trigger the victim execution. And let's suppose that depending on a secret bit of a cryptographic key, you're going to access either the entry 0 or 1 of the array. And for simplicity, in this example, let's say we access entry 1. Okay, and as you can see, the array at entry 1 was brought into the data cache. Finally, the attacker, by performing the reload step, it will measure the time of accessing every entry of the array. The first one will be slow because it's coming from DRAM, and it will be miserably slow, while array at entry position 1, it will be much faster, and the attacker, by measuring this timing difference, can infer what the victim actually executed. So again, this is a side channel. Looking at the time of execution, you can infer secret information. Things get really interesting when combining side channel with transient execution. That is a new fancy term for speculative execution, same stuff. Again, let's have a quick look at an example. Standard bound check array access. Let's say that the array size is low to get, is coming from memory or a complex mathematical operation. So the processor will not stop there. You will try to speculatively guess the outcome of this branch. And let's say that you guess on taken branch and you will execute the inner body of the branch. Again, the inner body of the branch is a simple load that will bring array X into the cache. And let's say that also later the processor discovers, oh damn, this was a bad speculation. We need to squash everything and revert the execution from the latest retard instruction. Here, as you can see, the array X is still in cache. So even if the processor never committed this instruction, there is still a trace in the cache, so a microarchitectural trace that an attacker can observe, again, by measuring the access time of every array entry. So it can even observe what the processor did speculatively. And thanks to this, many attacks were published in the past years. We started with all the huge family of Spectre on the left, Meltdown, then all the big class of MDS, microarchitectural data sampling, came in with many buffers to exploit. We have load value injection. We even go beyond a single core. There is crosstalk, an attack that works on different physical cores. where you can still do, say, channel attacks. And now, since we are in 2021, we are presenting our two new vulnerabilities that are floating point value injection and speculative code store bypass. And today we are going to present these vulnerabilities together with other type of machine clear.
All right. So let's take a step back first and think about what is the definition or what is the umbrella that under which we have branch misprediction and all these types of transit execution attacks. And in this case, Intel defines this sort of umbrella as bad speculation and defines it as the root cause of discarding issued microoperations on x86 processors. And it defines two main classes under this term. The first one is branch misprediction, as we saw earlier. So basically we have a branch predictor which mispredicts either the direction or the target of a branch. And the second class is machine clear, indeed, which is the one that we're going to explain today. And previously, all previous attacks, including and starting from Spectre, were using branch misprediction along with false or Intel TSX, which is the transactional memory implementation of Intel, to create new transit execution paths. And they were also continuing to rely on these three basically causes, and with different variations, but still mistraining a predictor, creating another type of fault, or aborting an Intel TSX transaction in a different way. But the same cannot be said about machine clear. Until our work, it remained a widely unexplored class of how we can create new transit execution paths without having to mistrain a predictor, let's say. And this is what we're going to explain today. So in this work, we performed the security analysis and the reverse engineering of the four main types of machine clear. The first one is self-modifying code. Then we have floating point, memory ordering, and memory disambiguation machine clear. These are four different causes of transit execution on modern CPUs. Two of which actually led us to have two new transit execution attack-based attack primitives. The first one is Speculative Code Store Bypass, which is based on a transient window created because of a self-modifying code. And then the second one is Floating Point Value Injection, which is created based on a transient window originated by a floating point machine clear. Then from floating point value injection, we were able to mount an end-to-end attack on the Firefox web browser, which allows an attacker to leak arbitrary memory addresses with a leakage rate which can reach up to 13 kilobytes per second. So here we're going to explain how we actually approach all these different types of machine clear during our reverse engineering and security analysis, and what are the main points that we actually focus on in order to understand the root causes of these events. First, we start to look at what is the architecture invariant at the core of each event, at each type of machine clear, and then how this invariant can be violated, and therefore creating a machine clear. Then what are the security implications of this invariant violation? And finally, how this violation can be exploited. In a nutshell, here, before we dive into the different types, a machine clear is basically a condition that unconditionally flushes the pipeline and causes to restart the execution from the last return instruction. So it's not like, for example, the misprediction of a branch where you basically revert the instructions executed inside the mispredicted branch, but it's anything that was in the pipeline from the moment that the machine clear event occurred. So the first type that we're presenting today is self-modifying code machine clear, which is based on a self-modifying code. So a self-modifying code is a program that stores instruction as data, modifying its own code while it's being executed. It's been widely used in malwares to unpack themselves when it's time to get executed. But now we're going to see them in a different way, in a different use case. So let's take a look at this snippet of code where we have two instructions. The first one is storing a no operation at the address of the following instruction, transforming the load from a load secret to a no operation. In modern processors, processors try to, in order to maximize the execution throughput, they fetch the code and execute well ahead of retirement to maintain the front end always filled with instructions. And whenever the case of an self-modifying code program occurs, in this case, the store that tries to modify the following instruction, the CPU is forced to flush its pipeline from the previously fetched, decoded, and executed instruction, in this case, the load secret, and consider the new instruction that is being stored, in this case, the no operation. So it has to fetch, decode, and execute the no operation. But since this detection of the fact that there has been an instruction that was fetched, decoded, and executed already in the pipeline, and now I have to replace it with a new instruction, that gives a window, creates a transient window where code is executed microarchitecturally and internal to the processor, and it, as we saw earlier, can leave traces that could be observable. So in this case, even if the CPU will never commit the load secret due to the new instruction that has to be executed, in this case, an operation, we can still observe the microarchitectural traces left by the transient execution of the load secret. So here, the architecture invariant of this type of machine clear is that store instruction always target data addresses. And this invariant is violated in the case of self-modifying code, which does exactly the opposite, targets code addresses instead. And this allows an attacker to transiently execute stale code, potentially under the control of the attacker. And in order to understand how we can exploit this in a more realistic use case scenario, we need to understand the attack primitive that this type of machine clear is actually providing us. So the attack primitive is called Speculative Code Store Bypass, and it's basically an attack primitive that allows an attacker to execute control code in a transient window originated by a self-modifying code, as we saw earlier. This primitive can be broken down in 3 main steps. But first, let's keep in mind that code and data views are 2 different views of the same exact memory, and they're always kept coherent between each other on modern processors. So the first step of our attack primitive is basically we try to JIT the code of a function f at the address of a function where the code of a function g is residing in memory, in this case as data, as we saw, because this is part of a self-modifying code program. And this store of the function f will cause a temporary desynchronization between the code view and data view, where in the code view we'll continue to have the code of function g that was already there, and in the data view we'll have the new code that we just stored. Then imagine if we now try to call function f, which we just stored, the processor will fetch the code that is residing at that exact address from the code view, from the front end. So it will fetch, in this case, the code of function g, allowing this transient execution of the code which was already residing on those addresses in the code view. At some point later during the execution, the processor will detect that there has been a self-modifying code and that it actually executed transiently stale code, and will eventually issue the machine clear, flushing its pipeline from the stale code, which is in this case is the code of function g, and will resynchronize or restore the coherence between code view and data view, resuming the execution from the new code that we actually intended to call in the first place, which is function f. We looked during our reverse engineering at different manuals. One of them is the Intel developer manual, which is suggesting 2 options to handle self-modifying code and cross-modifying code. And interestingly, if we look at option 1, it's describing the same exact steps of our attack primitives. So any software relying on option 1 to handle self-modifying code or cross-modifying code under the hood is basically creating an attack or performing an attack without knowing it. In fact, the 2 major web browsers, Firefox and Chrome, rely exactly on this option, which is there is no need to flush the instruction cache after we store new code, because they assume that the coherence between code view and data view is always maintained, also on the microarchitectural level, which is not true, as we saw in this case. So whenever Chrome or Firefox store new code, they are actually, and try to call it right after the store, they're actually executing stale code in the background. In fact, the use case, like JIT engines or web browsers in general, are not the only point where we can actually use speculative code store bypass. In fact, we can do this, we can exploit this in web browsers, operating systems, hypervisors, or generally any program that stores instructions or store codes and allows its execution before issuing a serializing instruction that will guarantee that there is the coherence between the data view and cone view is maintained. So this is how we can exploit an SMC machine clear, and this is the first type. The second type we're presenting today is memory ordering, and it's based on a total store order memory model, which is the one adopted by modern processors, which guarantees that all CPU cores see all memory operations as the program order, except in one case. If we have a store instruction followed by a load instruction operating on two different addresses, these two instructions might be reordered. Let's take a look at a snippet of code that would clarify this. So we have two processors, two cores. On processor A, we have two load instructions, then followed by a function call. And then on processor B, we have two store instructions. So following the definition of a total store order, the two loads on processor A cannot be reordered. They have to commit in that specific order. And processor B, the two store instructions cannot be reordered between each other. They have to commit in that specific order. Over time, let's assume that the first load in processor A is slow. There is a cache miss. It needs to fetch that data at address X from the DRAM. Again, that takes time. Processor A, though, does not want to wait till we actually fetch the data from DRAM. So what we will do internally, it will execute out of order the second load on address Y and all dependent instructions. And it will keep them in a state that is called ready to commit. Once the data at address X is fetched from memory, it will execute that load and commit all the instructions that it actually executed out of order internally. And then following the total store order. But let's assume that at some point, after the ready to commit instructions have been executed internally on processor A, processor B issues the two store instructions. So it's updating the value of X and the value of Y. At this point, the new values will be forwarded to the memory subsystem, which again will forward these new values to processor A. Processor A at this point cannot commit the ready to commit instruction that it actually executed previously, because those instructions are operating on the old value of Y. It cannot commit them as is, because otherwise it would be a proof that it actually executed out of order the second load compared to the first load, and then violating the memory ordering. So internally, the processor can do all sort of tricks to optimize execution, but architecturally, it cannot commit the instructions executed out of order, which in this case, the load on Y and all dependent operations. Otherwise, it would be violating. So it has to flush them, consider the new value of Y, re-execute them, and then commit still following the program's order. Otherwise, in order to follow the TSO. So as we can see here, the architectural invariant is that out-of-order execution always complies with the total store order memory model. And this can be violated in the case of a memory ordering machine clear. And this creates, again, allows an attacker to transiently leak stale data, which in this case was the old value contained at the address Y that was loaded out of order. In order to exploit this type of machine clear, there is a very strict synchronization requirement here between the two cores, which makes exploitation not very trivial. Now we'll see the other types of machine clear that we're presenting.
Thank you. So now things get, I would say, strange. I mean, speculation using floating points. Let's see why. Again, so in the IEEE standard for floating points, they decided to add a special representation for floating point numbers that are called subnormal, and they are used to represent very small numbers below that number there for the double representation. Again, to better explain this, let's have a look at an example. A simple floating point division followed by a floating point addition. And here, the issue is that the hardware, the floating point unit, is not capable of handling such a strange representation. So whenever you perform a floating point operation, the processor will blindly believe that operands and the results will reside in the normal floating point representation. So the processor, again here the FPU, will blindly compute the division results and send it to the subsequent operation. But let's say that actually the floating point division result is a subnormal number. The FPU will detect this later and must warn the CPU pipeline to stop the execution because the FPU provided a wrong result. So here, for example, the instruction in red will be removed from the pipeline. The processor will compute the floating point division, interestingly, in software, not in hardware, because again, the hardware is not capable. So there is a microcode assist injecting microops to perform the division in software. And then only after that, the correct result will be provided to subsequent instruction. That's also why these floating point operations are way longer compared to the standard ones. So here we saw that the floating point units, let's say, blindly operates on normal numbers. This makes sense because implementing in hardware, let's say, a floating point unit that handles subnormal would be way more complex. And to violate this invariant is super simple. You just need to perform a floating point division or, let's say, floating point operation that use subnormal numbers. And the security implication, as you're going to see, is that an attacker can transiently inject arbitrary values here on the red instruction, so on the subsequent instruction. And how can we exploit this? So here we managed to build an end-to-end exploit on Firefox. Okay, here we start by showing just the setup of the attack. On the left, we have the victim page on a different origin compared to an attacker iframe. So suppose that the right part is an advertisement, something like that. So before I said an attacker can inject transiently arbitrary values. So with a bit of brute forcing, we managed to find, to create a tool that we named the find operands, where you provide a value that you want to see on the speculative results of the floating point unit, and the tool will magically give you the results. Also, we built a test operand tool where basically provide X and Y is going to perform the division with these two numbers. For example, by dividing minus 1.6 by 4.9 to the power of minus 3.4. So the architectural results, the one that you actually see, let's say, on your calculator, will be minus infinity. That makes sense. But transiently, speculatively, the results will be completely different. And as you can see, the dead beef value that we wanted is exactly there on the speculative result. So an attacker can control what will be the speculative result. Also notice that the upper bits are set to FFFB. Why? Because dynamically typed languages like JavaScript in Firefox use numboxing. Numboxing, in a nutshell, is representing every variable as a floating point number. It sounds strange, but actually it makes sense. So the upper bits are used for the type of the variable. In this case, FFFB means this is a string variable. While the bottom bits, the deadbeef 000, is the payload pointer. So this single 64-bit means you have a string at this address. Okay, and now I think you start to see where the exploit is coming up. So if we use the X and Y parameters that we generated before, and we ask the JavaScript engine, look, is the output of the division a string? Speculatively, the processor will say, yes, it is a string indeed. And it will execute the red branch. But obviously, the division of a result, the result of a division is always a number, floating point numbers, okay? So architecturally, we'll execute the else branch. But again, speculatively, it's too late. We convince JavaScript the division result is a string. We control the pointer, so game over. By accessing, for example, the length attributes of the string, we are actually reading arbitrary memory. And again, using the Flush+Reload, so a standard state channel, we can leak arbitrary memory. One last step for completing the attack is to break SLR, because, okay, we have a nice primitive, we can leak arbitrary memory, but what are we going to leak? We don't know the address. And here again, a good, let's say, a superpower of transient attacks is that you cannot crash Firefox. You simply start reading all the addresses until you see something that you recognize. So we spray the Firefox process memory with 1 GB of known variables, a fixed value. And then we scan all the memory until we see our constant value. And then by slowly going up, we are going to find the address of the secret that we are looking for. So we also made a video to show the the exploit going on. Again, we start by spraying the memory because we need to break SLR. If I remember correctly, it was 1 GB of A allocated in JavaScript. Then we start a coarse-grained pattern search, so we leak every address after 1 GB, 1 GB, 1 GB. After a bit, we find our constant pattern. Then we do the fine-grained search to find the end of this sprayed memory. And after that, we break SLR. And now we are leaking all the process memory of Firefox. Here we are just printing, let's say, meaningful text. And after a bit, you will, exactly, here you see we are leaking the victim page memory. And here, please, think about it. So, from a floating point division, we confused JavaScript, that was a string, and finally leaking memory. This is kind of mind-blowing to me, at least. And also, if you run the exploit for a bit more, you're going to leak also JavaScript code that we didn't write. I don't know, is clearly JavaScript code, but yeah, you leak. Basically, you can leak all the Firefox memory, cookies, or whatsoever. Okay, let's go. Okay, to conclude on FPVI, so the exploit that you saw had a leak rate of around 13 kilobytes per second. That is quite high for this kind of attacks. Wait a second. Yeah, slides are hard. Not from the beginning. Sorry, just 1 second. This will help you refreshing all the contents. No, wait, if I start the video again, maybe it will be an issue. We were here. Nice. Okay, so what about the mitigation? So the obvious one is to disable this subnormal representation. But people don't like this solution because there are actually software relying on this spatial representation of floating point numbers. We also implemented a compiler pass to kill the speculative window when we detect this type of gadgets, and we get a 53% overhead. Well, actually, the, let's say, concrete solution that browser vendors used are either site isolation, so you cannot leak outside your process memory. And Firefox actually implemented mitigation where whenever you do a floating point operation, they are masking the upper bits, so they ensure that even transiently you cannot generate non-boxed variables. Okay, now the last type of machine clear. I promise it will be short. So when a load instruction is following a store instruction, which destination address is not ready yet, the memory disambiguation unit predicts whether the two instructions are aliasing or not. Again, an example to better clarify this. We have a store and then a load. Let's say that for some reason the store address is unknown. It's coming from a complex mathematical operation, from DRAM, who knows. So the processor would ask to a predictor, look, I would like starting performing the load, but I don't know the address of the previous store, so I don't know what to do. What should I do? Like, are you predicting that the addresses are different, or so that I can perform them out of order? Let's say that the predictor is called Memory Disambiguation unit. They predict, you can go ahead, let's perform the load even before the store. The addresses are not aliasing, are different. And then the CPU will be quite happy and it will perform the operation out of order. But let's say that actually the addresses were the same. There was a misprediction. So the processor loaded the stale data. So obviously now must load the hello value, the freshly new written value. So here the attacker can, let's say, perform a transient load where it reads stale data. Here the invariant is that the predictor unit never make a mistake, so always disambiguate correctly. To violate this, you need to mess up a bit with the predictor to induce a misprediction. The implication is that the processor leak stale data. And for exploitation, this was known as a Spectre variant 4, Speculative Store Bypass. So some exploits are already available. And here we are categorizing, as Intel suggests on the manual, as a machine clear rather than a Spectre attack variant. Today we presented 4 machine clear, but obviously there are many more, like conditionally masked move, some exception, the interrupts, other microcode assist. But for that we are not bothering you too much today. If you want, you can bother yourself by reading our paper. So if you want more information, please have a look. And now let's look at the results.
Okay. So we've seen very many types of machine clear. So let's take a look of what we saw so far. So a self-modifying code, modifying instructions, and therefore executing stale code. Memory ordering, violation of the memory model, and therefore leaking stale data. Performing a floating point operation, injecting wrong results, and manipulating the control flow. And the last one is memory disambiguation, which is leaking stale data by mistraining a predictor. Let's see how these types of machine clear perform compared to all previous known root causes of transient execution that have been widely used in previous attacks. So here are some numbers. In short, on the x-axis, we have the different mechanisms to create transient execution paths. And on the y-axis, we have 2 metrics. The top plot is representing the number of loads that fit inside a single transient window created by the different mechanisms. And the bottom plot is showing how can we leak, what is the leakage rate with a specific mechanism. Here we're using the Flush+Reload Attack as the architectural upper limit for leakage rate, which is the attack that we saw in the first slide as a side channel. Here we have TSX, PHT, and false. Those are the 3 main mechanisms that were used before this work to create a transient execution path. And now, TSX is only available on Intel, and it's not supported anymore on recent CPUs. And therefore, until this work, everyone was left with mistraining and branch history table, so another type of predictor, or causing a fault. Those were the 2 ways of creating transient execution paths. But now with this work, we have many more, and they're also available on AMD. So it gives, it widens the attack surface with these new discoveries.
Sorry to interrupt. Just before you carry on, I just want to make a quick announcement. Because we're running late, the next talk in the room, if you want to watch the ATM talk after this one, is going to be delayed until this is finished. So anyone who wants to do that doesn't have to rush off now. So sorry to interrupt you.
That's good. So as we can see here, we have a transient window created by self-modifying code. Inside that window, we were able to measure more than 160 loads executed inside a single window. These are 160 loads that will never commit, will not be seen at an architectural program execution. So you have 160 loads doing something in the background that will not be observed, if not through a side channel. And the other thing is, when it comes to a leakage rate with a floating point machine clear, we were able to reach more than 4 megabits per second. And this is thanks to the determinism of this type of machine clear which does not require to mistrain a predictor and try again. It's defined, like once you have X and Y, you perform whatever floating point operation you want, you're good to go, and you're sure that you will create a transient execution path. Finally, and this is the last thing, is that we try to classify all these types of root causes that we could use to create a transient execution path. And we start from the definition that we found in different patents and manuals, which is from bad speculation, which is, again, the highest hierarchy defining this behavior. We have two classes, control flow misprediction and data misprediction, which basically highlight, are we mispredicting or speculating over code, or are we speculating over data? And under each class, we have the corresponding subclasses with the corresponding predictors, while control flow mispredictions are failed attempts to operate or failed attempts to guess what are the next instructions that we're going to execute through the different predictors. Data misprediction are failed attempts to operate on data that has not validated yet, has not been validated yet. And then we have another subclass belonging to data misprediction, which is called exception, which represents all the architectural exceptions that has been widely used in previous transient execution attacks. And then we created a new subclass, which is called likely invariant violations, which represents all those architecture invariant that usually hold but occasionally fail, as we saw earlier in the case of floating point or an SMC. For example, on the floating point, as long as you're providing normal numbers, everything goes well, but as soon as you provide the normal numbers or subnormal numbers, things break, and that's when the invariant is violated. Finally, we have a last class, which represents interrupts, and more specifically hardware interrupts that we observed also creating transient execution path. You can read more about this in the paper. So we disclosed FPVI and SCSB to all major CPU browser and operating system vendors earlier this year. And we were informed that on Intel, for example, both FPVI and SCSB are affecting all Intel cores and Intel processors. Same thing is valid also for AMD, except that in the case of FPVI, we couldn't find an X and Y that were actually exploitable. But we were able still to inject an arbitrary floating point result in subsequent instructions. In the case of ARM, and specifically about SCSB, this couldn't work because the synchronization or the coherence between data and code is not built in as, for example, AMD and Intel, but it's left explicitly to the user. So whoever is writing code for ARM processors has to maintain this coherence between the two caches. But later we were also informed from ARM that some floating point implementations are vulnerable to floating point injection. Mozilla confirmed the vulnerability and released a mitigation with conditionally masking the NAND-boxed floating point results from Firefox 87 and on. And the Zen hypervisor mitigated SCSB, as we were suggesting, by issuing a serializing instruction after we store new code to make sure that code and data views are coherent. And when are we executing the new code, we actually executed that and not the state code that was in memory before. To conclude, bad speculation is not only caused by classic mispredictions and mistraining predictors, but also by architectural invariance violations, as we saw in all different types of machine clear. Architectural invariance can be exploited, creating new security threats like FPVI and CSB. And we think that defenses must focus on the wider class of root causes and the wider meaning of bad speculation. With this, I conclude, and you can find all the reverse engineering code, the exploit code, and the paper, and more information on our project page. And you can reach out to Twitter if you want. Thanks for your attention.
Excellent, really mind-blowing. And if anyone's managed to follow that enough to have any questions? No, I think you've broken the entire audience. Oh, we have one here.
So you said that Zen issued an advisory, and you said their fix was to issue a serializing instruction after things. How do they know if someone's making self-modifying code inside of a VM if, like, without monitoring every single memory write, how would they even know to issue that serializing instruction?
Sure. Yeah, if I remember correctly, it's not about what the user is doing. If I remember correctly, it was something about the startup of the VM, where the user was able to provide some piece of code that maybe was executed in a stale way. But yeah, it's, let's say, on the hypervisor level rather than the distinction between a guest and a hypervisor.
Sure. So they're mitigating it for their own code specifically,
Exactly.
not that it would stop anyone from doing this kind of thing inside of the virtualization system.
Exactly. Yeah.
Yeah, if I may add here, it's just whenever they are managing all the virtual machines, and for example, after some time you have virtual machines leaving code somewhere, and then you are trying to reuse that code memory again, you are risking to actually executing whatever was left from other machines. So it's more to prevent that there is complete isolation between what was left, state code provided by other virtual machines, and the new code that they're actually trying to execute in that moment.
Any other questions? Excellent. Well, thank you. That was a really great talk.
Thanks.